Hello friends, I welcome you in lecture number 6 on recurrence relations. In this lecture we are going to discuss solution of linear homogeneous recurrence relation with constant coefficients. We are going to solve linear homogeneous recurrence relation of degree 3 with given initial conditions. So we have discussed the method of solving this type of recurrence relations in earlier lectures, and if you have not seen earlier lectures, I suggest you to go and watch those lectures first, lecture number 1 to 5 on recurrence relations. Then only you will be able to understand this lecture. And if you have seen lecture number 1 to 5 on recurrence relations, then you might be familiar that to solve the recurrence relation, first we have to write down the characteristic equation corresponding to that recurrence relation. And to write down the characteristic equation, we replace an by r raised to n. In fact, we know that the solutions of this type of linear homogeneous recurrence relations are always in this form. So we can put an equal to r raised to n, and then by dividing with the lowest degree term in r, we will be able to write down the characteristic equation. Before that, I am considering all these terms on the left hand side, and I am rewriting the given recurrence relation. So this is minus 6 times a suffix n minus 1 plus 11 times a suffix n minus 2 and minus 6 times a suffix n minus 3 equal to 0. And I will consider an equal to r raised to n. So I am putting an equal to r raised to n in above recurrence relation. We have r raised to n minus 6 times. If an is r raised to n, an minus 1 is r to the power n minus 1 plus 11 times r to the power n minus 2 minus 6 times r to the power n minus 3 equal to 0. Now in this equation, lowest degree term is r raised to n minus 3. So we divide this equation by r to the power n minus 3, and we will obtain r cube minus 6 times r square plus 11 times r minus 6 equal to 0. After dividing this equation by r raised to n minus 3, I will obtain this characteristic equation of degree 3. Now if you are not if you don't want to write down all these things, then also it is fine. You can directly write down this step from your recurrence relation. So what you can do here, we know that recurrence relation has solution in this form, r to the power n. So if suffix of a is n, and here recurrence relation is of degree 3, so we will replace this n by n equal to 3. If degree is 3, then if we have an, we will write down r raised to n, that is r3. Similarly, we will replace this n by r, and if I have an minus 1, then I have r raised to n minus 1, that I will replace by r raised to 3 minus 1, that is r square. Similarly, r raised to n minus 2, and I will put n equal to 3, so I have r and minus 6 equal to 0. In short, we are replacing an by r raised to n, and this n is replaced by degree of recurrence relation, which is 3 here. So using that logic, you can directly write down this characteristic equation. For example, we again write down the characteristic equation using this logic. So what I have to first decide is what is the degree of recurrence relation. So here degree of recurrence relation is 3, and I have to replace n by 3 in r raised to n. I know that solution is in this form, an equal to r raised to n. So an minus 1 is r raised to n minus 1. Similarly, an minus 2 is r raised to n minus 2. And I am replacing an by r raised to n, and n is replaced by degree of recurrence relation. So an is replaced by r raised to n, and n is replaced by degree of recurrence relation. So degree of recurrence relation is 3, and here I have n, so I will write r cube minus 6. An minus 1 will be replaced by r to the power n minus 1, and n is replaced by 3, so I am writing r raised to 2 or r square, plus 11 times an minus 2 is replaced by r to the power n minus 2, and n is replaced by degree of recurrence relation, that is 11 times r, minus 6 times an minus 3 is replaced by r to the power n minus 3, and n is replaced by degree, which is 3, so I have r raised to 0, that is 1. So an minus 3 is replaced by 1, and this is equal to 0. So in this way we can directly write down the recurrence relation. We have to first decide the degree of recurrence relation, and then we replace an by r raised to n, and in r raised to n we replace n by degree of recurrence relation. So remember this logic, and you can easily write down the characteristic equation corresponding to given recurrence relation. So first I have to write down that this is the characteristic equation. The characteristic equation is r cube minus 6r square plus 11r minus 6 equal to 0. Now this is polynomial equation of degree 3 in r, and we have to find out values of r which satisfy this equation. So if you remember that if this type of polynomial equation has any integer solution, then it must be a divisor of constant term. Here constant term is minus 6, therefore if there is any integer solution to this characteristic equation, then that integer solution must be a divisor of constant term, which is minus 3 here. So if there exists any integer solution, then it must be a divisor of minus 6. So from this we may have the idea that we have to try for these values of r. So if I put r equal to 1, then let me check. If I put r equal to 1, I have 1 minus 6 plus 11 minus 6, that is 11 plus 1 12, and this is minus 12, that is 0. So that means one possible root is r equal to 1. Therefore r minus 1 is one factor of this left hand side. Once we decide one factor, and if we have third degree polynomial, then we can use synthetic division to decide the remaining two roots. For that I am writing one root which I have obtained by trial and error here, and here I am writing coefficients of r cube, r square, r and constant term, which are 1, minus 6, 11 and minus 6. Here we always start with 0. We add these two, that is 1 plus 0 is 1, and this we multiply with this one that we write here, then minus 6 plus 1, minus 5 multiplied with 1 is minus 5, 11 minus 5 is 6, multiplied with 6 is, and 6 minus 6 is 0. This is starting with coefficient of r cube, so this is going to be coefficient of r square, this is for r, and this is constant term. Therefore second factor is r square minus 5 into r plus 6 equal to 0, and therefore we have r minus 1 equal to 0, and r square minus 5r plus 6 equal to 0, and this is quadratic equation. I can easily find out the factors. This I can rewrite as minus 3r minus 2r plus 6 equal to 0. Here I take r common, here I take minus 2 common, and what I obtain is r minus 3 times r minus 2 equal to 0, and I have r minus 1 equal to 0. So after solving these linear factors, I have r equal to 1, 2 and 3. That means I have real and different or distinct roots of the characteristic equation of given recurrence relation, and therefore we can write down the formula for general solution. Therefore the general solution to the given recurrence relation is an equal to alpha 1 times r raised to n, that is 1 raised to n for r equal to 1, for r equal to 2, 2 raised to n plus alpha 3 times 3 raised to n, and 1 raised to n is 1. Therefore we have an equal to alpha 1 plus alpha 2 into 2 raised to n plus alpha 3 into 3 raised to n, and values of n are 0, 1, 2 and so on, and this alpha 1, alpha 2, alpha 3 are arbitrary constants, and we give this number 1. So here we have to mention that where alpha 1, alpha 2 and alpha 3 are arbitrary constants. Now we have to solve the recurrence relation together with given initial conditions. In the general solution we have infinite number of solutions depending upon the different values of alpha 1, alpha 2 and alpha 3. Out of those infinite number of solutions, we have to decide that solution which satisfies these three conditions. A0 equal to 2, A1 is 5 and A2 is 15. 2, 5 and 15. 2, 5 and 15, that is A0 is given as 2, A1 is 5, A2 is 15. Now this is starting from n equal to 0. If I take n equal to 0 in 1, I will obtain A0. Taking n equal to 0 in 1, we have A0 equal to alpha 1 plus alpha 2 into 2 raised to 0, that is 1, plus alpha 3 into 3 raised to 0, that is 1, and A0 is given as 2. A0 is 2, therefore we obtain alpha 1 plus alpha 2 plus alpha 3 equal to 2. We give this number 2. Then we put n equal to 1 in equation 1, that is in the general solution, and we write down the formula for A1. So I have to put everywhere n equal to 1, that is alpha 1 plus alpha 2 into 2 raised to 1, that is 2 alpha 2, alpha 3 into 3 raised to 1, that is 3 alpha 3, and A1 is given as 5. Therefore alpha 1 plus 2 alpha 2 plus 3 alpha 3 equal to 5. This is number 3. And we have one more initial condition. A2 is 15. So for A2 I take n equal to 2 in 1, and let's see what we get for A2 by taking n equal to 2. So I have alpha 1 plus alpha 2, n is 2, that is 4 alpha 2, and here 3 square, that is 9 alpha 3, that is alpha 1 plus 2 alpha 2 plus 9 alpha 3, alpha 1 plus 2 4 alpha 2 plus 9 alpha 3. Let me check again. If I take n equal to 2, this is 2 square, that is 4. So I have alpha 1 plus 4 alpha 2 plus 3 square, that is 9 alpha 3. and a2 is 15. Therefore alpha 1 plus 4 alpha 2 plus 9 alpha 3 equal to 15, and I give this number 4. Now we have to solve this system of linear equations in alpha 1, alpha 2 and alpha 3. So either we can solve by trial and error, or we can apply Cramer's rule if it is applicable, or we can use Gauss elimination method for solving system of linear equations. So here I am using Gauss elimination method to solve the system of linear equations in 3 variables or constants or real numbers alpha 1, alpha 2 and alpha 3. Now if you remember that to solve this system by Gauss elimination method, we have to first write down the augmented matrix corresponding to the given system, and then we have to convert that augmented matrix into row echelon form. So the augmented matrix of the system of equation number 2, 3 and 4, system of equation 2, 3 and 4 is, so here I have to write down first column for alpha 1, then second column for alpha 2, third column for alpha 3 and last column for the constants on the right hand side. So you can see in all the equations coefficient of alpha 1 is 1, therefore first column is 1, 1, 1. Coefficients of alpha 2 are 1, 2 and 4. So I am writing second column as 1, 2, 4. Coefficients of alpha 3 are 1, 3 and 9. So this is my third column 1, 3, 9, and constants on the right hand side are 2, 5 and 15. That is 2, 5 and 15. And we convert this augmented matrix into row echelon form. So for that we start with the first non-zero entry of first row, and using this entry we have to make these two entries 0. So I have to apply these two operations, taking minus 1 times r1, that is multiply first row by minus 1 and add in r2. Similarly multiply minus r1 by minus 1 and add in r3, and r2 and r3 will get change. So let me write r1 as it is 1, 1, 1, 2, and now I am operating this minus 1 into r1 plus r2, that is minus 1 plus 1 is 0, then minus 1 plus 2, that is 1, minus 1 plus 3, 3 minus 1 is 2, minus 1, that is minus 2 plus 5, that is 3. Similarly I have to multiply first row by minus 1 and add in third row. Minus 1 plus 1 is 0, minus 1 plus 4, that is 3, minus 1 plus 9, that is 8, minus 1 plus 15, that is 13. So this is the first operation for row echelon form. Now here we have first non-zero entry of first row, and all the entries below this non-zero entry of first row are 0. Now we come to the first non-zero entry of second row, and for row echelon form I have to make this 0 using second row. So here I have to consider the operation that multiply second row by minus 3 and add in third row. That means only third row will change, and we write down first two rows as it is 0, 1, 2, 3, and here 0, minus 3 plus 3 is 0, minus 3 into 2 minus 6 plus 8 that is 2, minus 3 into 3 that is minus 9 plus 13 that is 4. And you can see now this is in row echelon form. If you are not familiar with row echelon form, you can watch my lecture on row echelon form, and I have also uploaded lectures of solving system of linear equations in the course of mathematics 1. Now this is which is in row echelon form, and once we convert our augmented matrix in row echelon form, then we have to write down this system corresponding to row echelon form. That system is called reduced system. The reduced system is this first column corresponds to alpha 1, this is for alpha 2, then alpha 3 and constants. So first equation is alpha 1 plus alpha 2 plus alpha 3 equal to 2, then 0 into alpha 1, then 1 into alpha 2, 2 into alpha 3 equal to 3, alpha 1 plus 2 alpha 2 plus 2 alpha 3 equal to 3, 2 alpha 3 equal to 4, 2 alpha 3 equal to 4, and from this I will obtain alpha 3 equal to 2, and from second equation I will obtain value of alpha 2. Alpha 2 is 3 minus 2 alpha 3, that is 3 minus 4, which is minus 1, and from first equation alpha 1 is 2 minus alpha 2 minus alpha 3, and what is alpha 2? Alpha 2 is minus 1 and minus alpha 2 is 1, alpha 3 is 2, so 2 will get cancelled and we have 1. This means alpha 1 is 1, alpha 2 is minus 1, and alpha 3 is 2. So once we obtain these values of alpha 1, alpha 2, alpha 3, that we have to substitute in the general solution to obtain the required solution satisfying initial conditions. So here I have alpha 1 plus alpha 2 2 raised to n plus alpha 3 3 raised to n. So therefore we write down the final solution. The required solution, that is solution satisfying recurrence relation as well as initial condition, alpha 1 plus alpha 2 into 2 raised to n. Alpha 2 is minus 1, that is minus alpha 2 into 2 raised to n. Alpha 2 is minus 1, or let me write one more step, alpha 2 into 2 raised to n plus alpha 3 into 3 raised to n. Alpha 3 is 2, that is 2 into 3 raised to n, or we can rewrite as an equal to 1 minus 2 raised to n plus 2 times 3 raised to n. N takes the values 0, 1, 2 and so on. This is the solution which is required for our question, or this is the solution which satisfies given recurrence relation as well as initial conditions. If you wish, you can cross verify your answer also. You have to check whether your solution satisfies given initial conditions or not. Suppose I want to check whether A0 is according to given values or not, then I can put n equal to 0 here, and I have 1 minus 2 raised to 0, that is 1, plus 2 into 3 raised to 0, that is 1. So I obtain A0 equal to 2. Similarly, I take n equal to 1 and I have 1 minus 2 plus 2 into 3, that is 6, and this is going to be 5, and A2 must be equal to 15. So this is 1 minus 2 raised to 2, that is 4, plus 2 into 3 raised to 2, that is 9, and I have minus 3 plus 18, which is 15, and we are given these values of a0, a1 and 15, and that we obtain by taking n equal to 0, 1, 2 in the solution which we have obtained. That means our solution is correct. So this is very easy, but you have to take care while you solve this type of linear system, either by Gauss elimination or any other method. Otherwise this is very simple, but whenever you have this type of questions, they will ask it for 7 marks. So you must provide the method of solving these equations also, and here I have solved this by Gauss elimination method. If you wish, you can solve by Cramer's rule also or by any other method. There is no compulsion that you have to apply this method only. And here we have discussed recurrence relation of degree 3, and we have this real and different roots. So this is all about this session. We will continue with this type of recurrence relations in upcoming lectures. Thanks for watching.